Born in 1473 in the city of Turin, Poland, Nicolaus Copernicus would forever change the way that we perceive the nature and structure of the cosmos. His magnum opus on the revolution of celestial spheres would become the cornerstone of modern astronomy and still stands as one of the most influential scientific texts ever written. Copernicus proposed a heliocentric model where the sun, not the Earth, stood at the center of our solar system. This paradigm-shifting concept was a major factor in the development and the scientific revolution and would subsequently influence major figures such as Kepler, Galileo, and of course Isaac Newton. Even more than the theory itself, of special importance here is the particular method that Copernicus utilized, namely mathematical calculation and analysis. In this video, I will analyze the shift from the Ptolemaic to the Copernican astronomy. We will discuss some of the possible influences on Copernicus, as well as the reasons and justifications that he gave. Finally, we will explore how this episode in the history of science has set the stage for one of the most complicated and important questions within the philosophy of science, and that concerns the nature and status of mathematical reasoning. I hope that you enjoyed this video, and I look forward to hearing from you in the comments section. Before we get into a discussion of Copernicus's ideas and what influenced and shaped those ideas, I want to talk very briefly about science and astronomy prior to what is commonly classified as the scientific revolution. Now, there's a lot of issues within the history of science of classifying and demarcating when exactly the scientific revolution was. And like most other things that we label in history, these labels can at times be a bit arbitrary. And this is certainly the case with the scientific revolution. I say this because it's almost impossible to say when exactly the scientific revolution started, or the how and the why that it started. It's an immensely complicated phenomena that occurred. But most people would say that it had something in some way, shape, or form to do with Copernicus and the book that he published. Now, a quick point of clarification, because we're going to start off talking about astronomy and science before Copernicus. There's this idea that science itself was born during the scientific revolution, or that Copernicus is in this respect would be the father of science. I would fundamentally disagree with that reading of history. I would take a more loose understanding of what science is. I think that we can just understand science as the collection of knowledge, or an attempt to understand and comprehend the world around us. And if we take a rather loose definition of science, then science, broadly speaking, appears in most cultures throughout most of human history. Now, this might be a little strange view of science, because this also implies that science can be a discipline, can be a field that comes and goes, that there have been times when science has appeared in certain places, and in those same places where science has disappeared, that it's not this kind of like one and done thing. Science isn't this like monolithic entity that just suddenly appears and then stays forever. Instead, what I think we see happen is the appearance and reappearance of the sort of scientific institutions, the bodies and the structures that are able to support this sort of inquiry. And by my definition and understanding of science, again, it has appeared in most places throughout the globe. If you look at the origins of human civilization, places like ancient Egypt, ancient Mesopotamia, ancient India, ancient China, ancient Mesoamerica, that science appeared in some way, shape, or form in those areas. And in all of those areas, and in all of the cases where science appeared, what we would call today astronomy has been a chief fundamental concern of most peoples. And there's good reason for that. Probably the most important reason is that prior to the 17th and 18th century, there was no division or clear separation between what we identify today as astronomy and, on the other hand, what we would call astrology. In other words, prior to modernity, the Enlightenment, the modern period, whatever label you want to put on there, there was no clear demarcation, separation between astronomy and religious ideas and beliefs. Beliefs, astrology, loosely speaking, here we can, and again, we're talking about different cultures, different times, and different places, but loosely speaking, here is the belief that the quote unquote heavens, the area outside of the earth, the stars, the sun, the planets, that these had some sort of influence, whether we're talking physiologically, biologically, on things that happened here on earth. And almost always were also tied in with religious notions of God, gods, spirits, and spiritual forces that were at play. And again, we see this across the board. And if we're talking about the West, and if we're talking about major religions of the world, such as Christianity and Islam, so again, no clear separation between the two. And also to clarify, it's not like Copernicus himself is going to cause this separation. In fact, most of the scientists of the early scientific revolution, people like Copernicus, Kepler, and Isaac Newton, would make no difference between astronomy and astrology. In fact, most of them practice both. Most people during this time period, if you're studying astronomy, you're also studying astrology. They kind of went hand in hand with each other. And if we go even further back, as I said before, you have this connection between what is happening in and with the stars and the planets and the divine, that there's also this religious component in connection to it. Another way to think about the connection between the heavens and the earth is what's oftentimes referred to as the axis mundi. This sort of connection and relationship between the worlds appears in most indigenous religions across the globe. This is some imagery that I took from the lecture that I recently posted on YouTube regarding Mississippian culture and civilization. So this is on the left specifically, you have some Native American imagery, but this could also be applicable to if you're talking about places like ancient Egypt or ancient Greece. And this is the idea that the cosmos, the universe, as they understood it, getting back to this idea that there's no separation between astronomy and astrology, in most ancient cultures, there's also really not a clear separation or distinction between the physical and the spiritual. And especially with respect to the stars and the planets, it's almost always assumed that these entities were in some way, shape, or form related to or signifying the spiritual realm, that the stars and the planets are the realms of the gods, so to speak. What is above is divine. The sphere that we live on, the earth, the middle sphere, the middle axis, thinking about it within terms of layers, is the place that we dwell. It's also the place of change, of corruption, of life and death. And then, of course, at the bottom, you kind of have the underworld. Underworld imagery almost always symbolized in the forms of caves or waters and entities that live within this sort of dark realm as opposed to the realm of light, the realm of the sun. You can also see this signified in the duality of nature between the shift between day and night. But again, within this model, the movement of the heavens, even within the nighttime, the movements of the stars and the planets would have spiritual significance and did have spiritual significance. So much so that most of the ancient world wonders that you kind of think about, such as the pyramids of Giza or Chichen Itza in Mesoamerica, or in the video that I made about Mississippian culture, sites like Poverty Point or Cahokia, had these architectural elements that were lined up with astronomical locations. And this was to signify that connection between these different planes. Aside from the religious iterations and representations of cosmological entities, we start to see, beginning roughly 5th century in places like Greece, India, China, and Mesoamerica, a more sophisticated cosmology that starts to emerge. You still have this underlying spiritual significance of the heavens, but this starts to be merged with a more mathematical understanding and charting of the movements of these entities. Now, for the purposes of this conversation, ancient Greek astronomy, ancient Greek philosophy will be of a special importance here because this is what's going to have the biggest influence on Copernicus. In fact, if we're talking broadly here, thinking about the scientific revolution as a whole, the scientific revolution in one way could be understood as a response to Aristotle. This is due to the significance that Aristotelian philosophy played throughout the Middle Ages in Europe. And what we're going to see with the scientific revolution is a reaction and a rejection to Aristotelian cosmology and also Ptolemaic cosmology, which we'll explore here now. So Ptolemy was a Greek philosopher. Now, I use the word philosopher kind of loosely here. In the ancient world, there was no clear separation between philosophy and science. If you studied disciplines that today we would call science, such as physics, biology, chemistry, you were just called a philosopher. The term scientist doesn't appear until much later. I think not until the 19th century. I could be mistaken about that. Don't quote me on that. But in the ancient world, you were just called a natural philosopher if you studied nature, right? So you have a paradigm that emerges, which is going to be kind of roughly speaking a combination of Aristotelian physics and cosmology on the one hand, and Ptolemaic astronomy on the other hand. We're going to combine these two together to kind of explain what Copernicus is reacting to and the significance of his reaction. So Ptolemy was a Greek philosopher that lived in Alexandria, Egypt, not to be confused with the Ptolemaic dynasty, a dynasty of Greek rulers who ruled over Egypt after the conquest by Alexander the Great. But Ptolemy lived in Egypt in the city of Alexandria, and Ptolemy's system that he developed would become part of the dominant paradigm that would captivate specifically European thought for roughly the next 1,000 years or more. And again, what we're talking about here is a combination of Ptolemy and Aristotle. So what stands out about Ptolemy, as you can see on the picture on the left, the picture that my face is not covering up, this is the Ptolemaic solar system, the Ptolemaic universe. Now, I'm going to use solar system and universe kind of interchangeably here. If we're talking about ancient astronomy, the solar system is the equivalent of the universe. It's not a very big place. At least it's not big by our standards today when we think about how vast the universe is. For ancient peoples, the universe wasn't as big as we now know that it is. But what should stand out to you about the Ptolemaic representation, of course, is that it's the Earth that's at the center, a position that would become known as geocentrism. Geo meaning Earth, an Earth-centered universe, an Earth-centered solar system. And the moon, the planets, and the sun would revolve around the Earth. Now, I said that this is a combination of kind of two different philosophical systems and that Aristotle's a part of this. Where Aristotle comes into play is that some of the most widespread and common arguments for the non-movement of the Earth, for the Earth not moving, that came out weird, were provided by Aristotle, and also a justification for the motion of the sun and of the planets was also provided by Aristotle. This is not to say that there weren't heliocentric meaning sun-centered, sun, heliocentric, sun-centered universe. This is not to say that there weren't heliocentric models in the ancient world. Heliocentrism dates back to the Greek philosopher Aristarchus. He was the first that we know about to argue for heliocentrism. There's also a tradition within Islamic philosophy, specifically during the Islamic Golden Age. We'll come back to this because Copernicus was deeply influenced by Islamic astronomy. There were several Islamic astronomers who proposed heliocentric models as well. So I don't want us to be confused to think that Copernicus is the first person to come up with this idea. He's following a long tradition that goes all the way back to ancient Greece and that continued throughout the Islamic world that Copernicus kind of inherited. But nevertheless, for most of the Middle Ages, from since the writing of Aristotle, 4th century BCE, to Ptolemy, throughout most of medieval Europe, the Aristotelian Ptolemaic cosmology will dominate astronomy and scientific thinking. Arguments that Aristotle gave were so persuasive due to their appeal to common sense and common sense intuition. And this involves a couple of different parts. So let's talk about the motion of the Earth first. Aristotle argued that the Earth didn't move, and he gave a couple of very common sense down to earth. That's terrible. He gave a bunch of kind of common sense arguments for this. One is just our experience. It doesn't, I mean, just go stand outside and look up at the sky, right? It's the first argument. It doesn't feel like the earth is moving. It also doesn't really seem like the earth is moving. Kind of to add on to this, Aristotle proposed a simple experiment in which you go outside, get your bow and your arrow, and you shoot the arrow straight up. Where is that arrow going to fall? It's going to come straight back down from the position in which you fired it. There's a couple of reasons for this for Aristotle, which we'll get to here in a second, but part of the point in doing that experiment is that if the earth was moving, then if you shot an arrow up in the air and the arrow is going up and the earth is moving beneath it, the arrow ought to land in a different location, but it doesn't. Therefore, the earth doesn't move. Speaking of the motion of the arrow, Aristotle's physics provided one of the only cosmologies in the ancient world that explained motion. And motion's a problem. Motion's a problem, especially with respect to astronomy. And this is going to be super important for Copernicus because Copernicus does not have an explanation for motion. Copernicus does not have a reason, a justifiable reason to propose the heliocentric model other than the mathematical explanations that he's going to provide. But in terms of the ancient world, Aristotle provided some very good reasons for geocentrism. So going back to that arrow example, so you shoot an arrow, and it's obvious for most people that when you fire the arrow is going to slow. It's not going to go on forever. Right, the air is not just going to keep speeding through the air until it hits a target. That if there's no target in sight, if you go out into a field and you shoot the arrow, that the arrow will eventually slowly come back and fall down to earth. So why is that? Why does that happen? Aristotle's explanation for this has to do with his understanding of particular elements and what those elements are sort of drawn to. So Earth the element, not Earth the planet, although that's why it's called, anyway, Earth the element is drawn downwards, is brought downwards. It's the heaviest of the elements. And so this explains why material objects that are primarily composed of earth, now an arrow is composed of wood, but wood grows from the earth. So wood, the primary element of wood is earth. It's confusing, but hopefully follow along with me a little bit here. So the reason why the arrow slowly falls back down to earth is because earth is its primary element. The reason why when we jump up in the air, come back down to earth is because we're primarily composed of earth. And the reason why when we die, we decompose, we go back down to the earth, this sort of thinking. Other elements such as fire, why is it that fire moves upwards when you light a fire? Because fire, according to Aristotle, is primarily composed of air. So its natural inclination, its natural movement is to go back up into the air. So it would make sense within an Aristotelian view that the earth would be at the center because the earth is the heaviest. It's what's drawing things towards it. And then why the sun would be circling the earth because the sun is primarily composed of fire, according to Aristotle and for Ptolemy. Now, what really stands out about the Ptolemaic system is that Ptolemy would provide a tremendous amount of calculations to trace and to track the movements of the planets, the moon, and the sun through the night sky, or in the case of the sun, through the daytime as well. This was an immensely complex system that subsequent generations of scientists throughout the European and Islamic Middle Ages would add to, so much so that by the time that we get to Copernicus, this is a really sophisticated system. Now, one more thing about the Ptolemaic Aristotelian cosmology before we get to Copernicus. So we're talking about Earth-centered, and the moon, the sun and the other planets are moving around the Earth, but they're moving on. There's, again, going back to this explanation of motion. Why are they moving in the patterns that they do? It was believed that they're moving along these crystalline spheres that circle the Earth. These spheres are crystalline. We can see through them. We don't see the spheres themselves, but that the planets are basically rolling around these spheres in much the same way that if you roll a marble down like a grooved surface that'll follow the grooved surface, the planets are moving in a similar way. And these crystalline spheres also provide another explanation for a very obvious phenomenon that when you go out and you look at the night sky, yes, you notice planets like Mars and Venus, which move through the night sky, but you also notice hundreds of thousands of other stars that don't move. Why is that? Well, according to Ptolemy and Aristotle, the outermost crystalline sphere is the sphere of the fixed stars. These are stars which are kind of like stuck in place, so to speak, which is why when you look at the night sky, they don't move. And the interesting thing is that Copernicus won't really reject all of this kind of out the gate. So I don't want us to think that Copernicus is completely revolutionary in that regard. This is going to be kind of a cumulative effort that takes place throughout the 15th and 16th century. This system is so persuasive. It's not going to just be one person that kind of overturns this idea. Okay, I've already thrown around some of these terms, but I'm realizing that this is getting pretty dense in terms of terminology, especially antiquated terminology that's probably not going to be familiar for most people. So let me just walk through some of this real quick. I've already talked about geocentrism versus heliocentrism. Again, geo meaning Earth, geocentrism, Earth-centered solar system / universe, versus helio meaning sun, heliocentrism, a sun-centered solar system / universe. We talked about Aristotle and Aristotelian physics. We talked about Ptolemy, the Ptolemaic, named after Ptolemy. The Ptolemaic system is that geocentric system that dominated the European Middle Ages. Now, Ptolemy will also introduce some terms to astronomy that will stick with it. And these are terms that are describing phenomenon that are going to preoccupy Copernicus for most of his life. And the reason why he's going to propose the system that he does is in response to some of these. So let's get to it. Let me move my ugly mug so we can see better. Okay, so retrograde motion and epicycles. Going back to these spheres for a second. So you have the Earth at the center, and you have the other planets moving around the Earth in these sort of grooves that I mentioned before. It was the operating assumption here is that these spheres were perfectly circular. There's numerological and philosophical explanations for this. It was believed by philosophers like Plato and Aristotle that the heavens were a perfect place, going back to that axis mundi, that the heavens are perfect and the earth is corruptible, so the things that happen in the heavens must be perfect. This is also an idea that goes back to Pythagoras, that there are certain shapes that are perfect, the circle representing perfection in Platonic thinking. So the idea here is that when the planets moved around the Earth, they moved around the Earth in perfect circles. Again, this is not going to be an idea that Copernicus rejects. It's not till Kepler that we get elliptical orbits. Copernicus would accept that idea. But they're moving around the Earth along these crystalline spheres in perfect circles. Now, there's a big problem with that. And that problem is basic observation. So you go outside, let's say that you go outside every single night for a year and stare at the movement of the planet Mars. What you will notice eventually is that Mars will be continuing along the night sky on a kind of a trajectory that you could potentially map out, but that at some points in that trajectory, Mars will go backwards and forwards. That backward motion of the planet in the night sky is what Ptolemy would call retrograde motion, the apparent backward motion. Now, why do planets exhibit retrograde motion? It's because, according to Ptolemy, of epicycles. So you have these perfect circles, of the orbits of the planet around the Earth. And then on those perfect circles, you have smaller perfect circles that the planet will hit. So the planet's moving in a circle around the Earth, moving. It hits an epicycle, one of those smaller circles, and then it goes around that circle before going back on its original course. So retrograde motion is the apparent backward motion in the night sky, and the epicycle is the smaller circle in the larger orbit that the planet hits in its rotation around the Earth. It's this issue that's going to cause Copernicus to think about and look for alternative explanations. Now, that in and of itself, yeah, we're getting a little complicated, but it doesn't sound all that complicated until you consider all of this information as a whole and you get diagrams that start to look like this, in which we've mapped out the moon, Venus, Mars, the sun, and we have to account for the epicycles of all of those different planets. And if you add on top of that, this is just a visual representation. The purpose of creating charts like this is to track those planets. So the mathematics behind all of this gets really, really messy. And this is what's going to lead us to Copernicus in the 15th century. Okay, so like I said before, Copernicus's ideas are not just happening in a vacuum. They're not just appearing out of nowhere. There's some long history and tradition that's influencing Copernicus here. And I just want to take a second to point out some of those. So first and foremost, we have the Greek tradition, Greek philosophy. Now, who Copernicus is primarily responding to are thinkers like Aristotle and Ptolemy. So you can think of the Copernican system as a rejection of Greek philosophy, but it's also the Greeks who are influencing Copernicus. Again, this idea of some of the first heliocentric models are proposed by Greek thinkers, just in the same vein that some of the first geocentric models are. You also have some indirect influence by more Platonic thinking. This relates to that second box there, going back to the Renaissance and the Reformation. We have at really the beginning of the 13th and 14th century a sort of rediscovery of Plato and some of the other Greek thinkers by way of Islamic culture, by way of the Islamic Golden Age, in which we have the reintroduction of some Greek philosophical works back into Europe that's translated from Arabic into Latin. Ptolemy's work being one of those, but you also have this big reintroduction of Plato. I said 13th century. I'm pretty sure it starts in the 12th century. Somebody can correct me if I'm wrong there. And the reason why Plato's work is going to be important is because with Plato, we have this kind of Neoplatonic influence. Plato will place a great deal of emphasis on the form of the good. So if you read works such as Plato's Republic, the form of the good is represented as the sun. So the sun will start to take on new philosophical significance in that regard. So a heliocentric model, although it's rejecting kind of an Aristotelian understanding of the cosmos, will kind of be in line with more of a Platonic understanding of the cosmos. Now, I mentioned before the Islamic Golden Age. The Islamic Golden Age is a time period of roughly 800 years in which you have significant contributions in all the major areas of science, but especially in astronomy. Islamic scholars would preserve the work of Ptolemy, and like the European scientists of the scientific revolution, not all of them are just going to accept Ptolemy and Aristotle. You're also going to have a rejection of some of those ideas. So you also have some Islamic scientists that are proposing heliocentric models. Now, the extent to which Copernicus was aware of those Islamic models, we can't say for certain, but it's kind of in the air, so to speak. People are kind of talking about this. And we know that people are talking about this because the professors who are going to be teaching Copernicus throughout his educational career are going to be talking about heliocentric models. They're going to be talking about problems with Ptolemy. It's not something that just strikes Copernicus out of the blue. It's a problem that people have been noticing and will be noticing by the time Copernicus rolls around. That introduction of Plato, Ptolemy, and other Greek thinkers via Islam will also be a big cause of the European Renaissance, the Italian Renaissance, this sort of emphasis on humanism, textual translation, that will also play a role in shifting attitudes towards the past, especially towards dominant thinkers such as Aristotle, by introducing other people that may not have necessarily agreed with Aristotle. And finally, of course, we have the Protestant Reformation. The Protestant Reformation could be understood to be important in this regard because the Protestant Reformation is going to be a huge challenge to traditional power structures, specifically the power structure of the church. Now, that being said, to be clear and to be fair, Copernicus is Catholic. He's a Catholic canon of the church, will be for most of his professional career. But a lot of the people that Copernicus is talking to, because he's living in Poland, the Protestant Reformation starts in Germany, there's going to be a lot of cultural influence that's happening there. And some of his earliest supporters will, in fact, be Protestant, largely because there isn't really that kind of social obligation or stigma within the Protestant tradition like there will be within the Catholic Church, especially once we get to the time of Galileo. That's not to say that all of these Protestant thinkers would be receptive to Copernicus's ideas. They were not, as we'll see with Martin Luther, but it kind of lends itself to the challenge of tradition. Now, what I think is most importantly is the nature and the status of mathematics, because Copernicus is going to be doing something different with the math that lays behind all of this astronomy. Something different, not in this type or sort of math that Copernicus is doing. He's not going to be like Newton. Newton like invents calculus. Copernicus isn't introducing a new branch of mathematics. It's rather the emphasis that he's going to place on mathematical argumentation. What I mean by that is if you purchase, like if you go today and read Copernicus's On the Revolution of the Celestial Spheres, it's almost all math. It's charts, diagrams, and calculations of the movements of the planets, as opposed if you pick up and read Aristotle, which is mostly like logical argumentation. So the emphasis on the role and the use of mathematics within the natural sciences, what I think is the hallmark of the scientific revolution, is really going to be implemented and advocated for by Copernicus. This won't really catch steam until Galileo, as we'll see. A lot of people will actually push back against this, but Copernicus starts it. All right, so let me give you a little bit of background information about who Copernicus was, and then kind of gradually lead into how he came up with these ideas. So Copernicus, born in 1473, he dies in 1543. He'll publish his book kind of on his deathbed. Education-wise, Copernicus will go through a wide range of different educational backgrounds. He has a doctorate, yes, but his doctorate's actually in canon law, because Copernicus is a canon of the Catholic Church, canon law being the rules and regulations of the church itself and knowing and understanding those rules. That will kind of be his moneymaker. That's what he's employed by the church for. But because of his educational background, he's also going to be doing other things on a day-to-day basis, including the practice of medicine, astronomy, and astrology, all of which was employed on a regular basis by the church, as well as by wealthy patrons who the church would serve. So throughout his academic career, Copernicus would be exposed to the standard medieval curriculum of trivium and quadrivium, and a standard of that education was, of course, mathematics. Now, we don't know a whole lot of details concerning what exactly Copernicus was doing throughout his tenure as a university student and doctoral student. We do know that he was introduced to mathematics at Krakow, the first university that he went to, that he took several courses in mathematics, and that when he went to the University of Bologna, that he continued his education in mathematics, and that he also probably taught some classes in mathematics. So, and along with this, astronomy. So we know that this is something he's deeply interested in. We also know that at the University of Padua that he would study medicine. Now, with his study of medicine, and you oddly enough have a combination of medicine and astrology. This is medical astronomy. This is a practice known as medical astronomy that was popular in Europe at the time. Have a little brief quote here by a historian that kind of explains the idea here. The reception in 12th century Western Europe of Greek and Islamic technical astronomy and astrology fostered the development of medical astrology. The actual practice of medical astrology was greatest in the West between the 14th and 16th centuries. So Copernicus is kind of practicing and being exposed to the idea at the peak of their occurrence. And the rationale for this, going back to the basic idea of astrology, is that celestial objects have a direct impact on events and forces that happen here on Earth. Now, there's some basic observations that kind of lent itself to this sort of thinking. It was obvious to people at the time that things such as the cycles of the moon had a direct impact on things like tides. Now, again, they didn't know why the moon was having an impact on tides, but they could glean that there was some sort of connection. And if there was a connection between the moon and the tides, then that there was also to sort of strengthen the idea that there was a connection between the planets and things like people's physical health. So yes, Copernicus was exposed to medicine, medical astrology. We know that he would practice medicine in his position at the church. He would work at a leper hospital that was not too far from the church that he was employed as a canon at later on down the road. But that astronomy was something that he would remain interested in throughout his university career, and that's something that he would continue to be interested in his time as a church canon. And it's during this time that he spent as a canon that allowed him some free time to make astronomical observations, that he will start making notes and eventually compile his work, in which he will argue for the heliocentric model. So we know that a little later on in his life, Copernicus would compile some of his thoughts into a book, a pamphlet that he would call the Little Commentary, the Commentarialist. I'm probably butchering that pronunciation. I think that's how it's pronounced. That he would circulate amongst his friends and colleagues to kind of get their thoughts on. And it's in the Commentarialist that Copernicus will kind of outline, we see the basic ideas that would come to fruition in his later book on the revolutions of the celestial spheres. But this is what he says in the Commentarialist. So this is where we can start to see him putting his thoughts together. Copernicus says, yet the widespread planetary theories advanced by Ptolemy and other astronomers, although consent with numerical data, seem likewise to present no small difficulty. For these theories were not adequate unless they also concede certain equalizing circles. Those are the epicycles that we talked about before, which made the planet appear to move at all times with uniform velocity, neither on its different sphere nor about its own epicycle center. Therefore, having become aware of these defects, I often considered whether there could perhaps be found a more reasonable arrangement of circles, from which every apparent irregularity would be derived, while everything in itself would move uniformly, as is required by the rule of perfect motion. So it's the difficulties and calculations that derive from the epicycles is what starts to clue Copernicus in on the idea that there might be a better explanation. Now, as I mentioned before, we know that Copernicus was also having these sorts of conversations with his mathematics and astronomy professors while he was at university. So these sort of seeds have been planted. And once he gets down to the brass tacks of actually making these calculations and working through them, he starts to see that a better explanation might be possible. We see these explanations in the list of assumptions in Copernicus's Commentarialist that he kind of lays out. This is a kind of summary of the points that he makes. We see here the assumption that if we, instead of placing the Earth at the center, place the sun at the center, that we can actually get rid of a lot of these epicycles, and as a result makes the calculations themselves that much easier. Okay, so I mentioned before that one of the most important things, at least within terms of the philosophy of science, that comes out of this period of the history of science is this debate and the conversation concerning the nature and the status of mathematics. What this eventually evolves into, as we see between what a debate that happens between Kepler and Ursus, that I'll make a follow-up video related to this one on later on down the road here, is the debate over the status of astronomical hypothesis, especially astronomical hypotheses like the ones that Copernicus is making that are predicated solely on mathematical calculations. This is a debate that is still happening today, both within science itself and in the philosophy of science. This relates to a conversation between the distinction between scientific realism on the one hand and a different view called instrumentalism on another hand. We'll come back to that. I say it's still happening today. You see this a lot, especially around conversations such as string theory, especially, right? So string theory has a tremendous amount of mathematical support, but not a whole lot of empirical support. And as a result, this leads to some scientists questioning whether or not string theory is a legitimate scientific hypothesis. Now, the proponents of string theory would say yes, because of the mathematical reasoning that lies behind it. It's the same sort of debate that's happening with Copernicus. To illustrate this point, I want to read some selections from a preface that was put at the beginning of Copernicus's On the Revolution of Celestial Spheres. This was put in there by a mathematician named Osiander, who kind of frames Copernicus's work. Well, I'll just let Osiander explain. And this is probably, believe it or not, like one of the most controversial aspects about the book. Not necessarily, I mean, yes, you have the whole like heliocentrism thing, but this will spark a debate, like I said, that will continue on for generations after Copernicus. So this is what Osiander has to say. Since the novelty of the hypothesis of this work has already been widely reported, this is referring to the work that Copernicus previously had in circulation, in which he talks about heliocentrism, I have no doubt that some learned men have taken offense, because the book declares that the earth moves and that the sun is at rest in the center of the universe. Okay, it's this next part that has caused a lot of controversy since. Okay, for it is the duty of an astronomer to compose the history of celestial motions through careful and skillful observation. Then turning to the causes of these motions or hypothesis about them, he must conceive and devise, since he cannot in any way attain to the true causes, such hypotheses as, being assumed, enable the motions to be calculated correctly in the principles of geometry for the future as well as the past. These hypotheses need not be true nor even probable. So Osiander will be arguing for what we would call a form of scientific instrumentalism, in which he's basically saying Copernicus's ideas, Copernicus's mathematical calculations are more elegant and simple with respect to understanding the solar system, but that we shouldn't believe that these calculations have some sort of impact or an explanation of the physical causes of things. In other words, we might have the mathematics on one hand, but that physical reality may look and act completely different from what Copernicus is describing mathematically. Now, there are a lot of reasons for this, but the most obvious reason for this is that there's no observational evidence that Copernicus can draw from here. It's not like Copernicus has access to telescopes or satellites that he's building these ideas based off of observation or data that he's collected. His line of reasoning here is fundamentally mathematical and has little to nothing to do with the observations that he's making, which leads Osiander to say that these ideas might be mathematically true, but they need not be physically true. And this is a conversation that will spark a very famous debate between Kepler and a German mathematician named Ursus, and which will kind of culminate in the writings of Galileo, which we'll come to a little bit later. But I just wanted to highlight this conversation conversation to explain a little bit about why and how Copernicus developed the ideas that he was able to do, and to kind of set the stage for some later conversations. All right, well, I hope that you enjoyed the content of this video. Please let me know your thoughts below. Is this something that you still see happening within the context of modern science? Is this in a live debate, so to speak? And I will see you all next time.